In February 2009, two nuclear submarines carrying ballistic missiles collided head-on at the bottom of the Atlantic Ocean. Neither crew knew the other was there until their hulls physically scraped together. How did billions in sonar technology fail? To answer that, we must dissect the physics of acoustic silence, fluid displacement launch tubes, and cold launch missile silos. Because the reason these two submarines collided reveals a terrifying reality about modern naval engineering. Let's dissect it. Modern submarine warfare isn't about seeing, it's entirely about listening across a spectrum of underwater sound frequencies. Active sonar sends out a high-energy sound ping, but it gives away your exact position instantly to everyone nearby. Therefore, stealth submarines operate, strictly in passive mode, listening silently for the microscopic acoustic signatures of other vessels. To defeat passive sonar, the steel hull is covered in thousands of synthetic rubber anechoic tiles. These tiles contain microscopic air cavities designed to trap incoming sonar waves and dissipate their kinetic energy as heat. The second biggest source of underwater noise is cavitation. It is the formation and violent collapse of vapor bubbles on propeller blades. Modern submarines replace open propellers with shrouded pump jet propulsors, pressurizing water flow to completely eliminate cavitation bubbles. Internal machinery noise must be completely decoupled from the sea. Heavy machinery can resonate through the ship's hull. To prevent this, engineers use a suspended deck raft. Pneumatic lift air pressure creates a precise mechanical locking pulse. This raft rests entirely on heavy viscoelastic rubber mounts and hydraulic dampers, absorbing motor vibrations before they touch the hull. Even rigid fluid pipes act as acoustic highways. Every line connected to the raft uses flexible rubber bellows. Advanced propulsion systems replace mechanical steel bearings with active magnetic levitation, completely eliminating physical contact. The combined result is an acoustic signature quieter than the ambient background noise of the ocean itself. When a vessel becomes this silent, firing a weapon is the single most dangerous moment in its tactical mission. A loud launch reveals your position instantly. The ejection mechanism must be as silent as the submarine itself. Which brings us to the engineering physics of how a 2-ton weapon leaves a submerged hull without making a sound. A common misconception is that torpedoes ignite inside the tube. In reality, ignition inside a flooded tube would destroy the vessel. Instead, an internal hydraulic water ram uses a mechanical piston to drive water into the tube, forcing the weapon out silently. Only after clearing the hull boundary layer does the torpedo spin its counter-rotating propellers and activate its internal thermal engine. As the torpedo swims out, it unspools an ultra-thin fiber optic wire that remains physically connected to the submarine. This wire allows the submarine's massive combat computers to process sonar data and steer the torpedo silently without activating its own sonar. Only in the final seconds of the engagement does the torpedo activate its internal high-frequency acoustic seeker for terminal homing. And here is the critical part. Modern heavyweight torpedoes do not hit the target hull directly. They are programmed to miss on purpose. Detonating beneath the keel creates a massive gas bubble that lifts the ship out of the water, snapping its structural spine in half. When the high-pressure gas bubble collapses, the ship drops back down into a void, destroying its structural integrity using gravity itself. Vertical launch missiles operate on the exact same principle of cold ejection. Igniting a rocket engine underwater inside a silo is impossible. The gas pressure pops the waterproof capsule out of the silo, propelling it up through hundreds of feet of water. The capsule breaks the surface. Only when sensors detect open air do explosive bolts shed the nose cap and ignite the main booster. In mid-air, compact planar wings pivot outward as the missile transitions from vertical ballistic momentum to low-altitude aerodynamic flight. The missile drops to 10 meters above sea level, using radar altimeters to hide beneath enemy radar horizons. Using ring laser gyroscopes and jam-resistant GPS, the weapon navigates thousands of miles with zero active emissions. In the final terminal phase, an uncooled imaging infrared sensor matches the target's thermal silhouette against an internal 3D database. From silent hydraulic water ram ejection to mid-air rocket ignition, the entire launch process is engineered for zero acoustic footprint. Which brings us back to the Atlantic Ocean, in February 2009, and the collision between HMS Vanguard and Le Triomphant. Both vessels were nuclear ballistic missile submarines, running top-secret deterrent patrols at ultra-low speeds. Their anechoic tiles absorbed what little environmental ocean sound bounced between them, rendering both hulls functionally invisible. Compounding the problem, both submarines were operating inside a sharp ocean thermocline, a temperature layer that bends sound waves away. Because neither submarine was using active sonar, their passive hydrophone arrays were listening for sounds that simply did not exist. Furthermore, passive hull-mounted flank arrays have a natural acoustic shadow zone located directly along the rear propulsion axis. At 3 knots, two 15,000-ton steel structures slid through the ocean, moving entirely blind to each other's presence. They didn't explode. Their bows scraped past each other, crushing rubber anechoic tiles and bending outer hull casings. The 2009 collision proved the ultimate paradox of naval stealth. Engineers made these submarines so quiet they couldn't even avoid each other. Modern submarine warfare is an absolute masterclass in physical acoustic control, hydrodynamics, and force isolation. From cold gas VLS launches to hydraulic water ram ejection, every weapon system is engineered to protect the vessel's location.